back to Introduction to Continuity. We're at the point where we want to talk about, we've gotten some intuition, we've got the definition, we've got an example of continuity and discontinuity. Let me just talk about the three common kinds of discontinuities. Okay, so let me just actually make that a sub. Okay, so we've got a jump discontinuity, which is like the one pictured it, right? Where the limit from the left and right exists, but they're not equal. Okay, and this is most commonly seen with piecewise functions. Okay. To actually, with the formulas we usually use to create functions, sine, cosine, x squared, blah, 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 these guys don't really show up very often. But if you make a piecewise function, it's very easy to do this. In fact, it's rather hard not to have it have a jump. Okay. Infinite discontinuity. Those actually are the first ones we usually see. Those are vertical asymptotes. So, for example, the tangent function, y equals tan of theta. Let's just bring up the graph of that real quick. That has these points where on one side of like minus pi over 2, you're blowing up to 1 plus infinity, and here blowing up to minus infinity. You definitely can't draw that without lifting your pencil. Okay, so that's a pretty big deal. And then funky ones that we've actually been playing with a lot without hardly knowing it, although I've mentioned this a little bit, is removable discontinuity. That's something where it's actually rather hard to tell there's a kind of discontinuity sometimes, and that's where it just only fails to be defined at one point, and nothing else is weird. Okay. So it's a little hard for me to freehand right now, but for example, if I had this function, and if this were just a little open circle, if I had values for every x except 0.5, and there's just a little open circle, and there's just no value there. Or sometimes you can have an open circle here and then a closed circle at a different value. Those are both removable discontinuities. And I've mentioned that really, secretly, the tangent line problem is exactly this kind of discontinuity, because the functions we end up taking the limits of to calculate tangent lines are functions that are usually almost always totally fine, except at the one point where we really care about, and we have to sneak up on that point by taking a limit. Okay, now there's other things like infinite wiggliness. There was one book problem that we did see, and like it's in the book as well. It's like sine 1 over x, or I guess the example in the book is like sine pi over x to make it a little nicer graph. That's really weird. And that you usually think about more in like a more advanced analysis class. But it can happen. But these three are the most common. And these top two up here are the most obvious ones. The removals are a little subtle. So those are the kinds of discontinuities we see, like a jump, infinite discontinuities, very, very, very common. Again, it's not, if you want to be careful about these things and you want to really justify your work, you don't just look at it and say, oh, I recognize the picture, it's going to be this kind of discontinuity. You'd want to come back up to calculating a limit carefully and showing that either this doesn't exist, or this doesn't exist, or they're not equal. And then consequences of continuity. Okay, I'll be brief on this because I've got another video about the intermediate value theorem. But there's this wonderful theorem, and it's not as wonderful as when you first see it. It's not as obviously wonderful as you might hope, and partly because it seems so obvious. Although I was just reading an article that claims it's not obvious, but I think for us, let's not be too skeptical. All the intermediate value theorem says is that if you've got this property that remember the vague version of it, the rough version of it was, I can go from here, let's say to here on the graph, and if I graph that, I'm going to do that without lifting my pencil. Okay, that is this intuitive idea of how you recognize a graph is continuous. And let's suppose somebody said, I bet you that I can go from this value, from like x equals minus 0.5 and y equals about 3, and I can go from there to x is close to 1 and y is just a little bit bigger than 1. I bet you I can get from there to there without going through y equals 2. So let me graph y equals 2. Let me just construct a perpendicular there. Okay. I bet you I can get from here down to here and never go through that line. If somebody bets you that, you should take that bet, because they're not going to be able to do it. If it's a continuous function and I can go from here to here without lifting my pencil, then they're going to have to cross through that line. And it's surprising how deep and wonderful and useful that property is. And that's really called the intermediate value theorem. I have another video where we get more into particulars about how that's stated and how that's used and how it actually, gets into algebra and all kinds of stuff. But I wanted to mention that that's a big consequence of continuity that's going to be something we're going to discuss. Okay.